Hello everyone, welcome to our discussion of section 2.6. Now I know that I've mentioned this before, but at no other section more than this section, it's crucial that you, before we go through this video, or if you read the book, or if you attend the lecture in class, it's so important for you to please read through or skim through the textbook section before it is covered, either in this video or in class. It's so important in this section more than any other section we've covered so far. And I know I've been recommending it for every section, but particularly in this section, is extremely important that you do that. Otherwise, you may get confused. Your book has excellent text, excellent description of the topics covered in this section, and they have excellent examples that will help you a great deal in understanding this material. And of course, the rest of what I have been talking about goes for this section as well, which is take careful notes, attend the lecture, read the section before you attend the lecture or watch this video, take careful notes, and attend the class and review your lecture notes and solve all the problems you see in the text and the ones I see here, you see here in this video on your own without looking at the solutions. And then, of course, complete all the homework assignments by the due date and then review. Okay, so in this section, the main topic are the combining functions and composite functions. So combining functions is simple operations involving functions. I mean, so far, you've seen numbers being added or subtracted, or divided or multiplied. In this section, you will see functions being added or subtracted, or divided or multiplied by each other. As this happens, we call this combining functions. In other words, applying the operations, the four operations, addition, subtraction, multiplication, and division, to these functions, we call this combining functions. As this happens, the domain of the function that results is going to be different, or it could be different. Sometimes it could be the same, stay the same, but the domain of the resultant function could be different than the domain of the original function. So we'll have to do an investigation of that. The other thing, the other topic is the composite functions. In composite functions, we're not carrying out any of the operations with the functions that you saw, that you're going to see with combining functions. We're not going to add, subtract, multiply, or divide functions by each other. But with composite functions, we embed or replace one function inside another function. And then we want to know what is the domain of this resulting function. Again, with composite functions, we will place one function inside another function, and after that, we'll decide what is the domain of the resultant function. So, as far as the combining and composite function, as far as finding these functions, that seems to be okay with most of you. Most of you become, if not immediately, but shortly after, become comfortable with that process. But it's finding the domain that creates problem for most people, or majority of people. So before that, before we cover combining functions and composite functions, I want to say a little bit about how we find the domain for each category, for combining functions and composite functions. Okay? So, let's title this as domain of combined functions, of combined functions. Okay. So suppose we have a function f that has domain, let's call it A. Okay, so the function f, or f of x, has domain A. And the function, let's call it g, has domain B. Okay. In that case, then the combination of these functions in the addition operation, so then f plus g in x is equal to f of x plus g of x, and the domain is A intersection B. Okay, so what this is saying, when you add two functions to combine them, the domain of the resultant function or the combined function is the intersection of A and B. That means, i.e., where the domains A and B overlap. Okay, that's the translation of that intersection. Remember, A intersection B, when we talked about sets much earlier in the course, the intersection means where the common element between two sets. So where domain A and B agree with each other. They overlap with each other. Okay? The pieces that don't overlap will be excluded. Okay? Then, if we have the subtraction operation, when we combine the functions, then the domain, once again, is the intersection over overlapping domains. Okay. Third, we covered addition, subtraction. Then when we have the functions multiply, f times g, then the domain is the intersection of the domains. When we divide, then the domain is A intersection B, and g of x cannot be equal to 0. Okay, so that's the added. The denominator cannot be 0. We know that, right? The denominator of a fraction cannot be equal to 0. Okay, so that's the basic gist of how we find the domain of combined functions. Now, how about the composite functions? This is when one function gets embedded or placed inside another function. So, domain of composite functions and this is i.e. when one function is placed inside another function. I think at this point I should say something about the notation for composite functions too. So notice the combined function has to do with the operations involving functions, right? Combined functions, we talked about addition, subtracting, adding, subtracting, multiplying, and dividing functions, right? That's combining functions. The composite function or composition of functions has nothing to do with that. It has to do with one function is placed inside another function. So there is a notation associated with that. So suppose we have two functions, f of x and g of x, right? Both functions are a function of the variable x. Then this notation is a notation of the composite function. So then we have I guess I could call them by numbers, so I could list them, I guess. Let me list them. So 1, f, this hollow circle g, that's equal to f with the function g of x placed inside of it. So I'm just talking about the notation. I want to make sure that you understand the notation when you see it or read it someplace. F, this hollow circle G, F composition of G, means the second function is being placed inside the first function. So that function is going inside the first function, or like that. So you can either write it like that or like that. They both mean the same thing. Okay? Then, number 2, you could have G composition F. What does that mean? That means the second function, F, gets placed inside the first one. So F is the one that is being placed inside G. So that would be G like that. So you can either use this notation or that notation. It makes no difference. But you got to understand what this notation means. Or you could also say the composition of a function with itself. You can also do that. That means the function is placed inside of itself. So f as a function of f, like that. Or g as a function of g. Okay, so I just wanted to mention this notation. I prefer this notation better. I use both, but I prefer this one because it's more descriptive. It shows clearly that this function is inside that function, or f is inside g, and so on. So, when we get to this composition of functions, this is how we find the domain. the domain of a composite function, this is very, very important, is the intersection of the domain of the function that is being placed into the other function and the resultant composite function. Very, very important. See, up here, we said for the combined functions, we said that the domain is the intersection of individual domains of each function. Okay, pretty straightforward. But in combining functions, there are two domains. In order to, once you have the composite function, then you need to look at the domain of the function that was placed inside the other function. It's that domain that you should look at. And you should take the domain of that function and intersect it with the domain of the final composite function. In other words, you take the intersection of the domain of the function that is being placed in the other function and the final composite function. So you just can't write down the domain of the final composite function. That's not the case. You need to take the intersection of that point, that function, the final composite function, and the domain of the function that was placed inside another function to create the composite function. Okay? We'll do examples of this, but this is what I was saying. Your book has some excellent description and examples of these topics. And you do yourself a great favor and save yourself a lot of confusion by, or avoid a lot of confusion by reading the book first. Okay, we will do examples, but if you read the book, it's a huge help. Okay, so I wanted to talk about that before we dove into solving examples. Okay, so let's begin here. If we have two functions f of x and g of x, these two, then find this function, add them, so we're combining functions here, right? And find the domain. Before we find the domain, we know that the domain is the intersection of this domain and that domain, right? So what is the domain of the linear function? Are there any restrictions? No. The domain of this function is negative infinity to infinity. There is no restriction there. The quadratic function is a polynomial function. So, and polynomials always have a domain that is negative infinity to infinity. So as we find the addition of these two functions, the domain of the combined function is the intersection of these two functions, which is going to be negative infinity to infinity. So the addition of these functions is equal to x squared plus x minus 4. That's that. And the domain, it's going to be intersection of these two. So it's going to be negative infinity, comma, infinity. Okay. Part B, we're subtracting those two functions. Right? You can still see them on the screen. So that is equal to x minus 4 minus x squared. So that is equal to minus x squared plus x. I'm just putting these terms in the descending order of power. Minus x squared plus x minus 4. So that's the combined function. And the domain of this is the intersection of these two, right? Intersection would be negative infinity to infinity, like that. Multiplying the two functions, they're off the screen. Let me list them here. So f of x is x minus 4, and g of x is x squared. So we're dealing with these two functions, and we're multiplying them. So this multiplication would be x minus 4 times x squared. And that is, let's distribute, we get x cubed minus 4x squared. So that's the combined function, and the intersection of the domains, again, it is minus infinity, comma, infinity. Okay, so that's the domain of that. With division, we have to be careful here because we're going to form a fraction, and a fraction is not going to be it's not going to have a 0 in the denominator. It's not allowed. So with these two functions, right? Okay, so f divided by g is equal to x minus 4 divided by x squared. Now, we know individually each of these functions have the domain negative infinity to infinity, right? So whatever this domain, it has to intersect with those domains. So let's see. With this, we know that the numerator is fine, but the denominator can never be 0. So like that. And so x squared cannot be equal to 0, therefore x cannot be equal to 0, right? So take the intersection of the domain of this with negative infinity to infinity. So again, this would exclude 0. This is infinity to infinity minus or excluding 0. So in the intersection of this with the other domains, it will be negative infinity to 0, union 0 to infinity. So 0 is excluded, like that. I hope this is making sense. Okay. So here we have two functions given as f of x and g of x. Then find the addition or combined functions as added functions and its domain. So let's do that. Well, first of all, let's see what the domains of each individual function, what is the domain of each individual function, because the domain of each of these is going to be the domain of the combined function intersection of those domains, right? So the domain here would be when 9 minus x squared, when inside the radical is greater than or equal to 0. And that will be x squared less than or equal to 9. So if you move x squared to the other side, you have x squared less than or equal to 9. But I put the x squared on this side. It's just a habit to have my variables on the left side. Okay? And then x is less than or equal to plus or minus 3. So the domain here would be between minus 3 and positive 3. That's the domain for this function. I should actually put the bracket here. Sorry, brackets. So anything between and including negative 3 and 3 is part of the domain of this function. Okay? Then let's find the domain for this piece. We're going to need these. And then, so in here, 1 plus x must be greater than or equal to 0. Therefore, x is going to be less than or equal to, greater than or equal to minus 1. So let me correct that. So this has to be greater than or equal to minus 1. Okay? All right. So domain here would be bracket negative 1, comma, infinity. So let's find the combined function for each case. Here, f and g are being added. That gives us equal to square root of 9 minus x squared plus square root of 1 plus x. Right? So now this is a combined function, so we need to find the intersection of these two. What is the intersection of these two intervals? You can draw a graph about it if you want to, but the intersection would be between negative 1 and 3. Right? So D, or the domain, would be between negative 1, comma, 3. So this is the combined function right there. And this is the domain of that combined function. Okay? And we can do a graph of this. We don't have to, but just to show how this works, how this intersection business works. So one function had this domain from negative 3 to positive 3. Right? We have that. One function was that. From here to here. Another function is negative 1 to infinity. So negative 1, positive infinity. So negative 1 that way. Right? So where does that and this piece overlap? Between negative 1 and 3, which is what we have. Okay? On these, I drew the graph for this one, but I mostly avoided because the graphs tend to get really crowded and complicated. And anytime I've drawn graphs, it was always to make things easier to understand. But in this case, I think drawing graphs will make it visually more confusing. So I may avoid drawing the graphs unless I see that the graph is not going to be that crowded, or it could help. Okay, so this one, it wasn't too bad, I guess. But the point being that you have one domain doing that, and domain another function is doing that. Where do they overlap? In here. This is the overlapping piece. Let me thicken it. From here to here. Overlapping, or the intersection piece of the domains, both domains, right? That's the place they overlap. That's our domain for the combined function. Okay, here we're subtracting, right? So let's do that. Let me write the functions here so you can see them in front of you. So this is f of x equals square root of 9 minus x squared. And g of x is equal to square root of 1 plus x. So now we're subtracting. So we have f minus g, right? Square root of 9 minus x squared minus that. Once again, this is going to be the intersection of those two domains. And we already found that the intersection of the addition combined function is the same thing as the combined function that is the result of the subtraction of those two functions. So this is the combined function as they being subtracted from each other, and the domain will be, once again, bracket -1, comma 3 bracket, like that. Now multiplication. So you can still see both functions here, so I'm not going to write them down. So we have f times g, which is square root of 9 minus x squared times square root of 1 plus x. Okay, so let's multiply these together. What do we have? We know that if indices or the roots are the same, we can multiply the inside. That means we can do this. We can do 9 minus x squared times 1 plus x. Let's simplify the inside. I'm going to FOIL it. So we have square root of 9 times 1 is 9. 9 times x is 9x minus x squared and minus x cubed. Okay, and then we have so we have that, and then we have the there's nothing we can simplify here, and then so I'm not sure if distributing it made things a little more easier or not, but let me write this in. I guess keeping it in factored form would have been better. So keeping it here would have been better, because this way we can easily find where the domain is. So you could do this, it's okay, but to find the domain of the combined function, we already know what the individual domains are, which is what we found here. Now we need to find the domain of the combined function, and the factored form would make it easier for us to do that. Okay, that's all I'm saying. So keeping everything in factored form would have been easier. So let me work off of that. So working off of that, we have 9 minus x squared times 1 plus x must be greater than or equal to 0. This is for domain. Domain of the combined function. Okay, so we've talked about this before, right? We have here a factored form on the left. So let's find the boundary solutions. So 9 minus x squared equals 0. So that means x squared equals 9. Or x equals plus or minus 3. And then we have 1 plus x equals 0. So x equals -1. So these are our boundary solutions. That means I hope I have enough space on this paper to finish this solution, but let me draw my graph here. Let's draw a graph here so you can see it right there. So we have negative infinity to infinity with 0 here. Oops. Then let's place all these numbers on the x-axis or on the real number line. So we have -1 we have negative 3, and we have positive 3. Right? Can the domain be equal to these numbers? Yes, because the inside of the radical can be equal to 0. So I'm going to put a solid line over all of these, over that, and over negative 1. So we need to check 4 regions. We need to check here, 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 and here. And then whatever domain we find for this combined function, we need to take the look at the intersection of that with those 2 individual functions that we had that formed this. So let me, again, I hope I can put all the solution on this in the space that I have left. So test, so I'm just to save space, I'm going to just write down the test, and I'm going to put the result here, like that. So test a number in this region. Let's say -4. And put that number here to see if it's going to work out or not. So we have, well, let me write it down. It's better for you to have this rather than, I was trying to save space here, but it's okay. So we have 9 minus -4 squared times 1 minus 4. Is that greater than or equal to 0? So we ask, is that greater than or equal to 0? And the answer is -4 squared is positive 16. 9 minus 16, it's a negative number, right? It's negative 7. Negative 7 times negative 3, it's going to be positive, a positive number. Multiply that. So yes. So yes. So this here, in this case, this region is acceptable, part of the solution. What about -3 to -1? Right? That's 0 here. What about -3 to -1? Let's pick an easy number there, -2. So we ask if that's going to work out or not. So this inside cannot be negative, right? So we're looking at whether the inside is negative or not. So 9 minus -2 squared times 1 minus 2. And we're asking if the left is positive or negative. Well, -2 squared is positive 4. 9 minus 4 is 5. 5 times, this difference is -1. -1 times 5 is a negative number. So no, that's not going to work, and I'm going to say no. Okay, here. So far we have just that region. In between -1 and 3, in between that, we have 0. So test x equals 0. Will that work? So we have 9 minus 0 squared times 1 minus 0. Is that valid? So this is 9 is minus 0 is a positive number, 1 is a positive number, 9 times 1 is a positive number. Yes, so this will work. Yes, again. Now let's test some number in this region. Test x equals 4. Okay, so we have positive 4, right? 9 minus 4 squared times 1 minus or plus 4. We're asking if the left and the right, if this inequality is valid. So once again, 9 minus 16, that's minus 7. Minus 7 times 5 is minus 35. Is that valid? No. Minus 35 is not greater than or equal to 0. So no in this region as well. So according to this, the domain of the final combined function is between negative infinity, I'm looking at this graph, negative infinity to negative 3 bracket, union bracket, negative 1 comma 3 bracket, right? Is this the final domain? Well, it depends if what is the intersection of this. So take the intersection. I'm going to write it here so you can see it because it's off the screen. Take the intersection of that with bracket negative 3, 3 and bracket negative 1 infinity. Okay, the final domain, it's going to be the intersection of all of those. So we have negative 3, negative infinity to negative 3. That is outside of that. This is outside of that, right? Well, just negative 3 is part of both. Between these two, just negative 3 is part of both. The negative infinity, no. To all the way to 3, no. So we have negative 3. And then what about here? We have negative 1, comma 3. That is part of this interval, but not part of, well, let's see, partly these overlap, but there is no overlap between this and that. So this, and then negative 1, comma, infinity. Okay? So we have, let's draw a picture here. Okay, so if we draw the picture, we have, and then let's see, 1, 2, 3, 1, 2, 3. So negative infinity to negative 3 would be that region. Negative 1 to 3, that piece would be negative 1 to 3. So that area, right? And then what is the intersection of all of that with this? Well, is there an intersection between that and this? We have negative 3 to 3. So negative 3 to 3, yes. So there is an intersection between that and this piece, which would be from negative 1 to 3. So far, that is the intersection. Is there any other intersection? Negative 1 to infinity. So the intersection is just this piece. Between these two and this, the only intersection is negative 1 to 3. So the domain here would be negative 1, comma 3. Which, by the way, if you look at it in respect to part B and A, it's the same domain. Interestingly, these have nothing to do with each other because this was multiplication, but it turns out that that is the same thing as this domain. Okay? So there was no change from part A and B and C, they all had the same domain. Okay, so then we have these functions divided by each other. So let me write them here so you can see them. So f of x is equal to square root of 9 minus x squared, and g of x is equal to square root of 1 plus x. Okay, so now we're dividing, and we have to be careful because the g of x is going to end up becoming the denominator here. And once again, let me write down the domains for each of these, which we've already found. I'm going to write these domains for each of these functions on here. So this one had domain -3, 3. This one had domain -1, infinity. Okay, so let's form the combined function, which is that square root of 9 minus x squared divided by square root of 1 plus x. So here we have an added condition. We know that because, see, look at the domain of that g of x. It included -1, right? Because the inside of the radical expression could be equal to 0. But since that function ends up being the denominator of this function, we cannot have -1 anymore in that. So if we solve that for here, then 1 plus x must be greater than 0, not equal to 0, which means x greater than -1, or the domain here would be in the denominator would be parenthesis, not bracket, -1, infinity, and the domain here in the numerator would be the same thing as that, right? -3, 3. So if we take the combined function takes the intersection of this with all of that. Okay, so that means that the intersection of this is just coming from the denominator here, and for the combined function, so the combined function is this. And then we have, if you combine that with this, we have negative, let's see, we're going to take the intersection of that with this. So let's draw a graph like that, right? Because these two pieces are part of one piece now. So we got to make sure that all these domains agree. This one with that one, with that one. Okay? Okay, so we have 1, 2, 3, -1, -2, -3. So -3, 3 would be that piece, right? Would be that piece in here, from here to here. -1 to infinity, that would be that piece, right? All of that. -1 to infinity, take a look at the parentheses here. So it would be a hollow circle and going that way, right? So where do all of these intersect? What is the intersection for all these three pieces? For that one, and that one. The intersection then is domain equals parenthesis, not bracket, parenthesis, -1, +3, bracket. And there's the domain for that. Okay. All right. So let's look at another example. This would be number 3. We have these two functions, and we want to find the combined function f plus g. So this would be 2 over x plus 1 plus x over x plus 1, right? That's our combined function. Both have denominator x plus 1, x plus 1. By the way, the domain of this function, f, we know that the denominator cannot be 0. So x plus 1 equals to 0, x equals to negative 1 should be taken out of the domain, because x equals negative 1 would make the denominator 0. So the domain of this one would be negative infinity to negative 1, parenthesis, union, negative 1 to infinity. How about this one? The domain of that function, the same way, right? Just the denominator, the same way, the same domain is negative infinity to negative 1, union, negative 1 to infinity, right? So those ended up becoming part of the combined function. So the intersection of this domain with that domain is itself. Therefore, the domain of the combined function is also negative infinity, comma, negative 1, union, negative 1 to infinity. So everything except negative 1. That's what we're saying with this domain. And you can draw, if you wish, you can draw the graph as well. So we decided that negative 1 would not be acceptable right there. So let me put a hollow circle. So then what is acceptable is this piece, which is that, and this piece, which is that. So we're just excluding negative 1, that is being indicated by the parenthesis next to negative 1. Okay? All right, so subtracting those, it makes no difference in the domain, right? It makes difference in the combined function, but not its domain. So subtracting that, let me bring it down so you can see the functions right there. So we have f, which is 2 over x plus 1, minus x over x plus 1. So this is the combined function, and the domain, once again, is the same thing. Negative infinity, like that. Okay. So this is multiplication and D is division. And so it's on the screen, let me write down the functions again. So for this, f of x is equal to 2 over x plus 1. And g of x is equal to x over x plus 1. Okay, so now we're multiplying. Like that. What do we end up with? We end up with 2x divided by x plus 1 times x plus 1, right? And this is factored form, but we can rewrite this as 2x over x plus 1 squared. So the combined function is that. Okay, we already know that the domain for both of these is negative infinity to negative 1, union negative 1 to positive infinity, right? So let me write it down again. Domain for this and this is negative infinity, comma, negative 1, union negative 1, infinity. So that's for both this function and that function. So the new function, the combined function, I mean, has the same denominator squared, right? The numerator is fine. The numerator can be 0. 2 times 0 could be 0. But it's the denominator that is critical of what is happening here. And we have x plus 1, which is the same thing as squared. So the intersection of this domain and that domain is the same thing. Once again, negative 1 will make this, this combined function undefined. Therefore, the domain will be the same. The intersection of this domain with that is identical. That's what we're saying. Okay. All three functions have the same domain. Okay, so part D, and once again, because I want the functions to be on the screen as we go through this, so I'm going to write them here again. So f of x is that, and g of x is x over x plus 1. Okay, so now we're dividing f by g. Okay, let's do that. We'll do that. So we've talked about how to simplify complex fractions, right? The easiest way, I think, to simplify complex fractions is take the product of the terms that are farthest away from each other and put them in the numerator. Divide by the product of the terms that are nearest each other. Like that. So x plus 1 and x plus 1 cancel out because they're being multiplied. Let me say one thing here. So if you have, the reason we can simplify x plus 1, we can cancel them, it's because they're being multiplied. But please do not cancel anything like this. If you have something like this, it doesn't matter if it's plus or minus or plus or minus. As long as the terms are being added, we cannot simplify x plus, we cannot cancel x plus 1 with x plus 1. Okay, we could combine 1 with 2 or minus 1 with 2, but we couldn't cancel the this piece as a whole with this piece because it's being added or subtracted to another term here. We can only do what I've done here because these two are being multiplied and divided. There's a division here and there's a multiplication, so we can cancel them out. Okay, so the combined function then becomes 2 over x. That's the combined function. Now the combined function has a domain that is different than that, right? So let's see what the domain of this is. So here, x cannot be equal to 0. Therefore, the domain for this piece is negative infinity, comma 0, union 0, comma infinity. Is that the final domain for the combined function? No. We need to take the intersection of this domain with that domain, the domain of both of those parent functions. Okay? That's the domain of the parent functions. We need to take the intersection of that domain with this domain in order to find the domain of this combined function. So, two numbers should be excluded for sure. One is 0, the other one is negative 1 from the parent functions. So we need to exclude those two from the domain of the combined function. Therefore, the domain of the combined function is -infinity to -1, union -1 to 0, union 0 to infinity. Okay. So we can draw, if you wish, we can draw a graph of this as well. So both -1 and 0 should be excluded. These two numbers. So one piece is that's -infinity to -1. -1 to 0, that's that piece, excluding -1 and 0, and we do that with the parentheses around these two. And then the rest of that is 0 to positive infinity, which is that. Okay? I hope this is making sense. So what the moral of the story here is that the combined function, in the combined function, -1 is okay. But -1 is not okay in the parent functions. So we have to exclude the -1 as well, because those are the parent functions to this combined function. Okay, so number 4 is the straight domain calculation. Notice this function, we are not told that this function has parent functions. We're not told that this function is the result of the combined functions such and such. Because of that, the only domain that we have to look at is the domain of this function itself. We do not have to worry about the intersection of that domain with the domain of any parent functions. Okay, I hope that's clear. So here, we will look at the domain of this function just like we would look at the domain of any other function without any care what were the parent functions, because the parent functions were not provided to us. Or we were not told, I mean, we can create our own parent functions for this, but that's not needed here. All we have is a function, and we need to find the domain. Okay, so we know that x plus 7 can never be negative, right, for a square root. If we're looking for real number solutions, which is the case here. Here, we're not looking for complex number solutions. Okay, so we have x plus 7 greater than or equal to 0. This inside can be equal to 0 because it's in the numerator. Or it can be anything positive, but it cannot be negative, right? So let's solve that. So we have x greater than or equal to -7, right? So we have, given the numerator, we have bracket -7 comma infinity, but we're not done yet, right? So let's look at the denominator. So I guess, let me call this numerator, and then the denominator. The denominator is x minus 6, and we know it cannot be equal to 0. So x cannot be equal to positive 6. So in other words, here, according to this, we have -infinity to 6, union 6, positive infinity. So now, because these two form one function, we need to make sure that the final domain satisfies both these. So let's see. For here, for the numerator, we cannot have any negative number below -7. So we have bracket. Take the intersection of this with these two, right? -7, comma, and comma 6, right? comma 6. 6 cannot be part of the denominator, comma 6. Put a parenthesis there, union, parenthesis again, 6, infinity. So this final domain satisfies this whole function. Okay? It satisfies the numerator, it satisfies the denominator. Therefore, this domain belongs to the whole function. Okay? Okay, so here we have to find the domain of this function. Again, we are not told that this is a combined function. It's just one function, and we have to find the domain of the whole function without any regards to any parent functions. So the domain of this piece for square root of x, then x must be greater than or equal to 0. Therefore, for that piece, the domain is bracket 0, comma infinity. That's just for that piece. Now, how about that piece? So for that piece, we have square root of 8 minus x. So then 8 minus x must be greater than or equal to 0. Anything positive, right? Anything positive or equal to 0 is allowed. Then that gives us x less than or equal to 8, which means this is negative infinity, comma 8, bracket. So we need to, because we're looking at the whole function, we need to take the intersection of these two functions for the domain of the entire function. So this would be nice to draw, to use a graph. You don't have to draw the graph, but you can draw it any time that helps you better understand what's happening. So that one is saying all of that is the domain. This one says 1, 2, 3, 4, 5, 6, 7, 8. So that's 8. 8 and anything less than that. Like that. That one says that's the domain, right? So where do they overlap? Because if we're here, we're not satisfying that, and if we're here, we're not satisfying that. So the only place, the only intersection, the only set of numbers that will satisfy both pieces of the function is this overlapping piece right here, right? From 0 to 8. So the final domain is bracket 0, comma 8, and bracket again. Like that. Okay. So now we get to composite functions. The composite functions are, as we said, is when one function is placed inside another function. In this case, this notation, we talked about this earlier, it's saying evaluate the function g at 2, whatever the result, put it inside function f, which would be where the x is, right? So let's do that. So because we have a number, sometimes that is not a number, it's just an x. This is a number, so it's actually making things easier that we have a number. So let's first calculate what the function g at 2 is. So we have function g at 2 is equal to 4 minus 2 squared, 4 minus 4, 0. So the function g at 2 is 0. So now that 0 goes inside f, function f. Where can it go? X is where it can go. So function f at g at 2 is equal to function f at 0. I hope you are following this, right? We calculated function g at 2, it's 0. So the function f, composition of f at g and g in 2 is equal to f at 0, because g at 2 is equal to 0. So I just replaced that with 0. Okay, so then let's replace x in f with 0. So we have -4. So that's the final result. Okay. So this one is the opposite. It's the function f evaluated at 2, then that result is placed inside g. So let's first find the function f at 2. Function f at 2 is equal to 7 times 2 minus 4. So we have 14 minus 4, or 10, right? That's function f at 2. So therefore, g at f at 2 is equal to g at 10. I hope you're following what's happening here. Okay, g at 10. So let's put in g, let's replace x with 10. So we have 4 minus 10 squared. So we have 4 minus 100, or minus 96. Okay, I hope this is all. I hope you're able to follow all this. If not, please ask about it. Okay, so given two functions f and g, we want to find composition of f and g at -2. So this is using a different notation than that, but it's the same thing. Here and here, we know that the second function always gets placed inside the first one. So here g goes inside f, here f goes inside g. Okay, so what we're really asking here is composition of f at g at -2. These two notations are exactly identical. So let's first find what g at -2 is, and then we're going to substitute that for x inside f. So g at -2 is equal to 2 minus -2 squared, 2 minus 4, right? Minus 2 squared is 4. 2 minus 4 is -2. So f, that is equal to that, and that is equal to -2 is equal to f at -2. Okay, so let's substitute that. 5 times -2 minus 4, that's -10. This is -4, and we have -14 as the final result. Okay. This one. This is exactly the same thing as g composition of f at -2. These two notations are identical. So what this is saying is evaluate the function f at -2, and then that result goes inside function g to evaluate g at that point. So first, let's find this piece. The function f at -2, let's plug in for x with -2, which is 5 times -2 minus 4. That's -10 minus 4, and we get -14. Okay, negative 14. Now, G, composition G of f in negative 2 is equal to G at negative 14. I hope you're following what's going on here. And then equals, so let's, in G, we're going to replace x with negative 14. We have 2 minus negative 14, right? That's our function right there, G. 2 minus 14 squared equals 2 minus 14 is, squared is some positive value, right? I don't want to guess at it. So let me calculate this. So it's going to be negative 14 squared. It is 196. So 2 minus positive 196, which is minus 14 squared is my positive 196. So this will be 2 minus that, it will be minus 194, like that. Okay. Okay, so we have two functions f and g, and we want to find function f, composition of itself, f again, at negative 1. So what they're asking is find f at negative 1. These two are identical. So that is being asked about. So let's find the value of function f at negative 1. So f at negative 1, let's plug in. 5 times negative 1 minus 2 is equal to minus 5 minus 2, or negative 7. Now, that notation, f at negative 1 is equal to f at negative 7, right? Because we found this piece to be negative 7. So we're going to do that. Then that is equal to 5 times negative 7 minus 2. So we have minus 35 minus 2 minus 37. Okay. All right. So can I keep? Let's see. Yeah, you can see them all on the screen this way. So this one is saying take the composition of g, function g with itself at 2. In other words, we have to do this, g at 2. These two are exactly asking for the same thing. So let's find the function g at 2 first. G at 2 is equal to, this is our function right here. So 3 minus 2 squared would be 3 minus 4, that's equal to negative 1. So therefore, let me write this down. G at 2 is equal to, so composition of G with itself at 2 is equal to G. We already calculated this piece. It's negative 1. Okay, so we're going to put it back into G and recalculate G. 3 minus 1 squared equal to 3 minus, this is positive 1, right? The inside, minus 1 squared is positive 1, and this gives us 2. Okay. Okay, so here it says, given these two functions, find the composition in X, and then the domain of the new composite function. So in this case, G is the second function, right? So we know G goes inside F. When we talked about, at the beginning of this video, when we talked about the domain of combined functions and composite functions, we said that for the composite functions, the final domain of the composite function is equal to the intersection of the domain of the function that is going to be placed inside the other function, so the intersection of this domain with the domain of the composite function. Okay, just remember that as we calculate all of this. So this notation is equal to f at g in x, right? So that means all of g goes inside f. Where can it go? It can't go inside 1. It has to go where x is. So 1 over 2x plus 8. Okay? So this is our composite function. Now the domain of this has to be the intersection of the domain of this and the domain of the function that was placed inside f. Not f, but the function that was placed inside f. So g of x so we have the composite function. What we're doing now is finding the domain of that. So the function that was placed inside f was that, g of x, right? 2x plus 8. What is the domain of this? Everything is included, right? No restrictions. So the domain of this is negative infinity to infinity. Okay? Now, what is the domain of the composite function? That one. So that domain of that is 2x plus 8 cannot be, when it's 0 we have trouble, right? Because this whole fraction or this whole function is undefined. So x, when x equals minus 4, we have trouble. So the domain of that piece, or the composite function, is negative infinity to negative 4 union negative 4 to infinity, excluding negative 4. Now, if you take the intersection of this with that, what do you get? You get itself. You get this again, which is fine. I mean, in this case, it's working out like this, that if you take the intersection of this domain with that domain, you end up with this. But a lot of times that may not be the case. A lot of time when you take the intersection of this with that, you don't end up with this. So be careful in cases like that. As a matter of fact, I think we may have examples like that here in this set of worksheet. But in this case, it just happens that when you take the intersection of the composite function with the function that went into it to form it, that was placed into the other function, you get this back. So it's okay. We keep that as the domain of the composite function. No problem with that. But we have to go through this verification process, is what I'm saying, because not always it works out like this. Like that. So that's the composite function, and this is its domain. Okay. So composite function, this time the second function is f. So f must go inside g. So what we have here is g like that. That's the function we're looking for. Okay. Is equal to f goes inside g. So we have 2 times 1 over x plus 8. And so we end up with 2 over x plus 8. So this is our composite function. Okay, that's the final result. Now, what function went into which function? It was f that went into g, right? So what is the domain of the function that went into another function? So let's find the domain. So that was the function f of x. I want to keep everything on the screen like that. So f of x was 1 over x. And from this, we know that x cannot be 0. So the domain of this function, the function that went into the other function, is equal to negative infinity to 0 union 0 infinity, right? So compare that, the domain of this, right, 2x plus 8, that has the domain, again, x cannot be equal to 0, right? So domain is negative infinity to 0 union 0 to infinity. So take the intersection of this one and that one. Take the intersection. I want to be clear. Cases like this worry me. Maybe I should change these examples and find other ones. Cases like this worry me because when you take the intersection, you end up with the same thing. It might give some people the impression, oh, I can just stop right there and take the domain of the function that went into the other function as my final domain for the composite function. And that's not true. You must go through this verification process. You must intersect the domain of the function that went into the other function with the domain of the final composite function to find the final domain for the composite function, which in this case is itself, again, that. Negative infinity, comma 0, union 0, comma infinity. And let me move this like that. Okay, so that is the domain of the composite function. Okay. Okay, so here we have these two functions, f and g, and we want to find this composite function and its domain. Notice that g is the second function, right? So g goes inside f. So we need to know what is the domain of g. So let's find that out first. So the domain of g, we know that from this, x equals 0 is fine because that's in the numerator. It's not going to harm anything. If the numerator is 0, it's not going to harm anything. It's the denominator that we cannot have 0. So x plus 7 equals to 0. X equals negative 7 would make the denominator 0. We need to exclude the negative 7 from the domain of the function that is going inside another function. So domain of that is negative infinity to negative 7, union negative 7 to positive infinity. Okay, now let's find the composite function. So that g goes inside f. So 7 divided by, all of that should go where? Where x is. So x divided by x plus 7, right? So we end up with a complex fraction. And the complex fraction here, 7 has denominator 1. And as I've mentioned before, the easiest way to simplify a complex fraction is take the product of the terms that are farthest away from each other and put that in the numerator, and take the product of the terms that are nearest each other and put that in the denominator. I put that one in red because we don't when the denominator is 1, we don't write it, right? And the denominator of any digit is 1. So here it makes a difference because we need to know what terms are nearest each other and what terms are farthest away from each other. Okay, so then the result of this is that the composite function would be equal to 7 times x plus 7 divided by x. So this is our full composite function. Now the numerator, as we said before, is fine. We don't have to worry about it as long as it doesn't have a square root or another fraction. Okay, we don't have to. So in this case, there's no square root. There's no other smaller fraction. So this is just okay. With nothing to worry about. But this x, notice that this x here means that x cannot be equal to 0. So because of that, the 0 should be excluded, right? That and that. So that's just this, what I've said here in using interval notation means simply that exclude 0. That's all it's saying. Now, is that the final domain for the composite function? No. We need to intersect this, what we have here, with the domain of the function that went into another function. Not f, but the one that went into it. So that tells us that -7 should be excluded. Is that excluded here? No. We need to ensure that it's excluded. So to do that, let me see, how do I, so you take the intersection of this, take the intersection of this and that. And what do we end up with? I'll try to fit that there. So we end up with -infinity to -7 union -7 to 0 union 0 to infinity. There is the domain. There is the domain of the final composite function. That is the domain of that. Not these two. We need to take the intersection of them, and that's the intersection, that's the domain of the composite function. Okay, so here for part B, and let me write down those functions because we need to look at them as we go through this exercise. Like that. Okay. So what's the difference here between this and part A? Well, in this case, f is the second function. So f is going inside G. So what's important is the domain of this as well as the domain of the composite function. We need to take the intersection of those two. So let's find the domain of this. We already kind of know it, but for the sake of the notes, let's write them down. Let's write it down again. So because f is the one that goes inside G, let's see what the domain of it is. So x cannot be 0, right? So -infinity to 0, union 0 to infinity. Now, let's find the composite function. We need to find the composite function and its domain. So this is, so G composition f in x is the same thing as G composition of f in X. That's what they're asking us to find. So that means all of f goes inside G. So all of this goes inside G. Where can it go? It should go where X's are. So we have 7 divided by X divided by 7 over X plus 7. Okay? We're not done yet because we need to simplify this, right? So let's do that. So I'm going to take the common denominator here. Let me put it in a corner here. So this common denominator, 7 over X plus 7. The denominator here is 1. The common denominator is X, right? So we have to multiply the numerator by X and the denominator by X. So we end up with 7 over X plus 7X over X, or 7 plus 7X over X, right? So now we're going to put all of that, and we can factor it, right? 7 times 1 plus X over X. That's all of that is in the denominator here. Like that. So we have 7 over X in the numerator divided by 7 times 1 plus X divided by X, right? So let's see. Let me just make sure here everything is all right. So yes, it's okay. All right, so let's simplify this. So what we did here was just to find the common denominator and then that. Okay, so the way to simplify this is take the product of the farthest terms from each other, so 7 times X, and put it in the numerator, and take the product of the nearest terms and put them in the denominator, like that. So X and X cancel out, 7 and 7 cancel out. So the composite function, G, let me write that here, G and F in X is equal to 1 over 1 plus X, right? That's the composite function. Now, for the domain of this, we need to find the domain of the composite function and intersect it with the domain of the function that went into it. Okay, that will be the final. So let's find the domain here. For this one, we know that 1 plus X, when that's 0, we have trouble. So when that happens is when X equals -1. So we need to take the -1 out of the domain. So for this, we have -infinity to -1 union -1 infinity. Is that the final domain? No. This is a composite function. We need to intersect this with that. So take the intersection. Let me zoom out a little bit so you can see both. I want to show both. Okay, you can see, at least now you can see both, right? So take the intersection of that, which is the function that went inside another function, and that. Take the intersection of that and that. What do we end up with? We end up with domain. So -1 and 0 should be excluded, right? -1 and 0 should be excluded. So the domain is -infinity to -1, union -1 to 0, union 0 to positive infinity. That's the domain of the composite function. Okay, that. This is the composite function, and that is its domain. Okay, which was found as the intersection between that and the function that went inside another function. Okay. For part C, let me once again. So this is taking the composition of G and G. So I want to write the function G here. So f of, the G of x. G of x is equal to x over x plus 7. Okay. So now G composition G is this. It's exactly that. So G goes inside of G. That means the intersection of the domain of G with the final composite function is the domain of the composite function here. So we already know the domain of this, right? The domain of this function G is negative infinity to negative 7 union negative 7 to positive infinity. And x, whatever it is, it's okay in the numerator. In the numerator, we're fine. So let's find the composite function. We need to put G inside G. So that'll be x over x plus 7. That's the numerator. Divided by x over x plus 7 plus 7. Okay, I took G and put it back in G. Where can it go? It can only go where x's are, right? Here and here. So all of G where x was, now you have that. All of G went where this x is. Now you have x over x plus 1. So of course the denominator, we need to take the common denominator, right? So the common denominator here, let me do that in a little calculation here. X over x plus 7 plus 7 over 1, right? Common denominator. And then we have to multiply this. The common denominator is x plus 7, right? It's clear from here. So let's multiply this by x plus 7 because this is just 1. We don't have to multiply this fraction by anything because the denominator is already equal to the common denominator. But this here, 1 multiplied by the common denominator, right? But we can't do that to the denominator and not do it to the numerator as well. So x plus 7. Okay, so what do we end up with? We end up with x over x plus 7 plus 7 times x plus 7 divided by x plus 7. So add the denominators are common, add the numerators. So we end up with x plus 7 times x plus 7 divided by x plus 7. Let's simplify the numerator, right? We have x plus 7x, I'm distributing the 7, plus 49, 7 times 7, divided by x plus 7. Then we have 8x plus, this is all just to take the common denominator, 8x plus 49 over x plus 7. Okay, so let's plug this in to what we had up here. So now we have x over x plus 7, right? That divided by all of this. all of this. So we have, let me move this up a little bit like that. So we have 8x plus 49 over x plus 7. Okay, so let's just the way I explained before, to simplify the complex fraction, take the product of the terms that are farthest away from each other and put them in the numerator. Take the product of the terms that are nearest each other and put them in the denominator. So x plus 7 times 8x plus 49. So x plus 7, x plus 7. Then x over 8x plus 49. Right? So now that's the composite function. So let's write it. G composition of G in x is equal to that. This is our composite function. Now we already know the domain of G, function G, which went inside G, right? Let's keep that in mind. Now let's find the domain of the final result. We know that 8x plus 49, when that is equal to 0, we have trouble, right? The whole function is undefined. We cannot have that. So let's find the value of x in a situation like that. And we can't simplify this anymore. So the result here is negative infinity to negative 49 over 8 union negative 49 over 8 to positive infinity. So we need to take the intersection of this and this, right? Negative 49 over 8, that is a little bit or it's 6 something, right? Minus 6 something. So minus 6 something is larger than negative 7. So the way we take the intersection is as follows. So let me put the arrow here, here, and here. So when I post these lecture notes on Canvas, you can see it better all at once. But here, I don't want to zoom out more than this. Maybe I can. Maybe I can zoom out a little more. And a little more. Yeah, that would be... I don't want to make this smaller than it already is, because you might not see it in the video. I'm not sure. So basically, we're taking the intersection of this domain with this result. Okay, and we end up with this. So we have the domain of the composite function, which I've boxed here. The domain of this function is as follows: negative infinity to negative 7 union negative 7 comma negative 49 over 8 union negative 49 over 8 comma infinity. Like that, okay? Okay, so that's the domain of this composite function. Like that. Okay, so thank you again for persisting through this video, and for now, have a nice day. We've wrapped up, what section was this? I forget. It was section, let's see, it was section 2.6, so we wrapped this up, and have a nice day for now, and I will see you next time.